The only machine that ever carried humans to the moon would collapse under its own weight if you stood it up on Earth. You're probably thinking that's a flaw, a rushed job, corners cut under Cold War pressure. It wasn't. This spacecraft was deliberately built too weak to survive the planet that made it. Its walls in places were as thin as 3 sheets of foil, and a screwdriver dropped from waist height could punch straight through. And yet NASA bet 6 lives on it, twice on the same mission, because that fragility was the answer, not the problem. But why did NASA build it that flimsy on purpose? Why the astronauts flew standing up with no seats at all? And why its landing escape engine had no backup? None of it is what you'd guess. Start with the number that ruled everything. When Kennedy committed America to the moon in 1961, nobody had built a machine to land there, and the deeper the engineers dug, the worse the arithmetic got. To land 2 men and lift them off again, you need fuel. To carry that fuel, you need a bigger structure. A bigger structure weighs more, so you need more fuel to move it, which needs more structure, a spiral that ate itself. Every single kilogram added to the lander demanded roughly 4 more kilograms of propellant back in the rocket that launched it off Earth. The Saturn V, one of the most powerful machines ever flown, stood as tall as a 36-story building, and after all that fire and thunder, the slice of it that actually touched the moon could weigh no more than about 15 tons. That's it. 15 tons for a descent stage, an ascent stage, 2 astronauts, their life support, their fuel, and everything they'd carry home. To put that in scale, that's less than the weight of 2 loaded city buses to do the hardest thing humans had ever attempted. So Grumman, the company that won the contract, faced a trap with no obvious way out. Build it strong enough to feel safe, and it would never leave the ground, or build it light enough to fly, and it looked like something that couldn't possibly protect a human being. Their first instinct was the one you'd have: make it a proper spacecraft. Early designs had 5 legs, big pressurized cabins, thick walls, and heavy seats bolted to the floor, a machine that looked like it belonged in space. And every version failed the same test. The scale wouldn't balance. Engineers stripped, and still the numbers came back red. One senior designer said the mass problem haunted them daily. They'd claw back a few kilograms in one system only to watch another grow. For months, it genuinely looked like the lander might be the piece that made the whole moon landing impossible. Not the rocket, not the heat shield, but the small, fragile thing at the very tip. And that's when the thinking flipped. The engineers stopped asking how to make it survive the trip and started asking what the trip actually required. Look at where this machine would spend its working life. It would separate in orbit, descend, land, and take off, all in the vacuum of space and on the surface of the moon, where gravity is 1/6 of Earth's. It would never fly through an atmosphere. It would never face wind, never face rain, never carry its own full Earth weight for even 1 second of its mission. So why build it to endure forces it would never meet? That single realization unlocked everything. On Earth, a structure has to hold its own crushing weight and shove through thick air. In vacuum, at 1/6 gravity, those loads mostly vanish. So the walls of the crew cabin were shaved down to aluminum in places just 0.5 millimeter thick, thinner than 2 stacked credit cards. Where you saw that shimmering gold and black skin on the outside, that wasn't armor at all. It was insulation, dozens of layers of mylar and Captain foil, some sheets thinner than a page of a book, trapping the moon's brutal temperature swings from more than 100 degrees Celsius in sunlight to below -150 in shadow. The foil didn't hold the ship together, it held the heat out. The structure underneath was so light that on Earth, under full gravity and air pressure, it truly would buckle. It was engineered to survive only off the planet. But saving weight on the walls wasn't enough. The scale still hadn't balanced, and now they went after the crew. The astronauts wouldn't get seats. That sounds reckless, and here's where it stops being what you'd expect. Seats are heavy. The frame, the mounts, the reinforced floor beneath them all cost precious kilograms. So they were deleted. The 2 pilots would stand, held by a harness of cables and straps, for the entire descent and landing. And when engineers ran it, standing turned out to be better. The final approach lasts only minutes. Standing up close to the 2 small triangular windows, the commander could lean in and look almost straight down at the landing site, tracking boulders and craters he'd never have seen strapped into a reclined chair. Removing the seats didn't just save mass, it let the windows shrink too, which saved more, and it gave the pilot a sharper feel for the machine on the controls. The weakest choice on paper made them fly better. Then came the decision that could kill them. After landing, the top half of the lander, the ascent stage, had to fire its engine to lift off and rejoin the command module orbiting above. If that engine failed to light, there was no rescue. No second lander, no way home. 2 men would die on the moon and the world would listen to it happen. You'd expect NASA to answer that terror with redundancy, a backup engine, a spare, layers of insurance. They did the opposite. The ascent engine had no backup at all, and it was made as brutally simple as physics allowed. It burned hypergolic propellants, 2 chemicals that ignite the instant they touch, with no spark, no igniter, no pump that could jam. Open 2 valves, let the fluids meet, and combustion is automatic. The insight was cold and correct. A second engine means more valves, more plumbing, more mass, and every added part is one more thing that can break. A single engine with almost nothing in it to fail was statistically safer than a heavy redundant one the mass budget couldn't carry anyway. So they poured their effort into making one burn perfect and flew with no plan B. Because the simplest possible thing was the safest possible thing. Piece by piece, that's how the scale finally balanced. 0.5mm walls, foil skin, no seats, one dead simple engine. Every radical strip down flowed from one truth the early designers had missed. This machine only ever had to work in vacuum and 1/6 gravity, so it was built to survive only there. The fragility wasn't a compromise forced on them, it was the entire strategy. The Lunar Module is the only crewed spacecraft in history deliberately engineered to be destroyed by the planet that made it. And that's precisely why it could reach the moon at all. 6 times it landed and lifted off flawlessly. The screwdriver-thin ship worked. And then, in April 1970, it was asked to do something it was never built for. 200,000 miles out, an oxygen tank in Apollo 13's command module exploded. The main spacecraft was dying, losing power, air, and water, unable to keep 3 men alive for the days it would take to get home. The lunar module was still attached, and it was never designed as a lifeboat. It was built to keep 2 men alive for 2 days. Now, it had to keep 3 alive for 4, on the way back from a landing that would never happen. But the very things that made it look flimsy saved them. It was so lightly loaded, so simple, so full of the improvisation margin that comes with a machine stripped to essentials, that the crew could stretch its power, its oxygen, and its engine far past the numbers on the spec sheet. They fired that no backup ascent engine to swing around the moon and aim for Earth. They huddled in the freezing cabin as the temperature fell towards 0, and the paper-thin craft carried 3 men 250,000 miles home alive. The lunar module proved that reaching another world was never just a question of power. Success came from removing everything that wasn't absolutely necessary, designing only for the environment the spacecraft would actually face, and trusting physics over intuition. Half a century later, engineers faced a remarkably similar challenge, but in reverse. Instead of building the lightest possible machine to land on another world, they had to figure out how to bring the largest rocket ever built safely back to Earth, turning a controlled crash into a routine landing. To understand how SpaceX solved one of the hardest landing problems ever attempted in aerospace engineering, click this video.